This lecture is going to help you graph simple functions. My goal will be to help you see a picture whenever you see a formula. This is what all good mathematicians and physicists do. We're going to begin at a very simple level, learn about axes and the coordinates of a point. Let's begin with these two perpendicular lines, one of which I shall call the x-axis and the other the y-axis. Sometimes this is called the horizontal axis and this is often called the vertical axis. Where the two meet is the origin. And now let me mark off equal distances on the x-axis. So that's 1, 2, 3, and so forth. And on this side, -1, -2, -3, and so forth. Similarly, on the y-axis, I shall mark off equal distances on both sides. So this is -1, -2, -3 along the y-axis. Take any point that lies in this plane. So for example, this one over here. To reach this, I have to move one unit of distance along the horizontal axis, 1 unit along the vertical axis, and so I write this as 1, 1, and that is the coordinate of the point that's over here. Well, let's take another example. Let's take this point over here. Now, I had to move 2 distance units along the x-axis and 1 along the -y direction. And so this is the coordinate 2, -1. And similarly, over here, well, let's say here I have -3 units along the x direction, 1 or let's say half unit along the y direction. Now, these are coordinate axes, and the first quarter or the first quadrant is all the points that are contained over here. That's the second quadrant, third quadrant, and fourth quadrant. Now I've removed the markings, but let me take any point over here, let's call it P1. It has coordinates x1 and y1, which means I go x1 units along the x-axis, y1 units along the y-axis. And let me take a second point, call it P2, which has coordinates x2 and y2. Okay, to get from P1 to P2, I must move like this. How far? Well, that is x2 minus x1. And then I must move from here to here, and that distance is y2 minus y1. Now, if I was to move directly from P1 to P2 like this, that distance, let me call it L, then you see I have a right angle triangle over there, and you know from elementary geometry that L squared is going to be the sum of the squares of this right angle triangle. So x2 minus x1 squared plus y2 minus y1 squared. That means that given any 2 points in the xy plane, we are able to find the distance, or rather the square of the distance, in this manner. Now let's see what it means to make the graph of a function f of x. So as you remember, a function is something that takes in a number x and produces a number f of x. So if I was to take this pair x and f of x, these would be the coordinates of a point P. So let's say This over here is the point P, and its coordinates are x and f of x. All right, now I can take a whole bunch of these points, and this might be just one of them. And so in general, the function f of x could look something like this. Every point on this represents a pair of numbers, the value of x, and x is of course the horizontal coordinate, and f of x over here is the vertical coordinate. Now sometimes one writes y is equal to f of x. This is just to make things a little more compact, in which case one is plotting the points x and y. So any point over here on this curve has coordinates x and y. In other words, the graph of a function is the ordered pair x, y. Ordered because x has to come first, y has to come later. And what is y? Y is simply the value of f at the point x. Let's take a very simple example of a function to be graphed. So here is f of x equals x squared. Let me make a little table over here. X and the value of f at the point x. Take x to be 0, f is 0, half, the square of that is 1/4. Take 1, 1, 3 by 2, 9 by 4, 2, 2, etc. And now notice that if I put x equal to minus x, so if I have either plus or minus half, the answer is still 1/4, and I could put plus or minus everywhere over here. So let me plot these points. Here's the first point. At half, the value is 1/4, so that's about over here. Then at 1, I have 1, and I'll skip the other one. At 2, at 4. And now if I go on this side, I have these points here and here and so forth. Now, and of course, the ones over here and here. If I join up these points, I will get the graph. Now, rather than do it myself, I have a little magic pen that will do the job for me. It just makes it look nicer. I could do it by hand too. So let me begin with that. And you see that it is going through all the points that I had made. Now let's look at the graph of f of x equals x to the power 4. Here is what it looks like. My magic pen comes. You see that when x is equal to 0, f of x is 0. As it increases very slowly until it reaches 1, and then it goes very, very fast upwards. Now let's do that again. You see that here it is really very, very flat. On this side, it is very, very steep. So this is another example of an even function. Let's now look at x to the power 6. You see it's become even flatter close to the origin, and x to the 8 now is yet flatter, x to the power 10, and we could keep going on this. Let's quickly look at f of x equals x squared again. So here comes my magic pen, and at x equals 0, it has its minimum. You can see that here is where it becomes 0. But now, let me make a function that's very closely related to that, and that would be f of x equals x minus 1 squared. What does that look like? as you can see, it's almost the same, except that now the minimum, or where its value is 0 in this case, is at x equals 1. And now I can do this same thing for x minus 2 squared, x minus 3 squared, and you see that the function is simply shifting over towards the right. Well, let's keep decreasing that quantity. And so here is x plus 1 squared. You notice that at x equals minus 1, it has value 0. And of course, x plus 2 squared will be there, and so forth. Let's now look at another function of x. Here, f of x equals x cubed. Now, this is a function that's very negative when x is negative. It's 0 when x is equal to 0 and very positive when x is positive. Let's ask our magic pen to plot this. So as we come from large values of x, which are negative, we move towards 0. And now at 0, the function is 0, of course. It rapidly increases and goes off to plus infinity. Now notice that here, close to the origin, the function is quite flat. Now this is an example of a function that's odd. An odd function is such that if instead of x you put minus x, then the function itself changes sign. Obviously, when x goes to minus x, this function over here is changing sign. Let's take now f of x equals x to the power 5. Here the curve looks similar, but it's so much flatter near x equals 0 and goes up faster. Here I have f of x equals x to the power 7. Watch this. And now f of x equals x to the power 9. Let me quickly compare all of them once again. X cubed, x to the 5th, x to the 7th, and x to the 9. Of course, not all functions are going to be either odd or even. Here's an example of one that is neither odd nor even. F of x is x cubed plus x squared. The x squared part is even, the x cubed part is odd. And now let's see what this graph says. You will expect, of course, that when x is very negative, the x cubed will dominate. And so it's going to come up much like f of x equals x cubed did. But now at x equals minus 1, it crosses 0 and then becomes 0 again at x equals 0, increases and then just scoots off to infinity. You could have anticipated this, of course, because when x is equal to minus 1, you see that f of minus 1 is minus 1 cubed, which is minus 1 plus 1. And of course, that's 0. Let's now look at the simplest odd function that there is. Here, f of x equals half of x. This is a straight line, and let's follow it through. So as x increases, you can see that y also increases, and it's steadily increasing as x increases. Correspondingly, if I decrease x, y also decreases. Notice that when x is equal to 1, y is equal to half. So it's half divided by 1. In other words, the pencil went 1 unit here and half unit up. Here it went 2 units here and 1 unit up. So here we have 1 over 2. Let's look here. Here the pencil went 3 units up and 6 units to the right, and so forth. In each case, we have half, half, and half. This half is the slope or the gradient of this straight line. Slope is also called gradient, and in this particular case, it is half. In general, one would have, let's say, a point over here, call it P1, and its coordinates are x1 and y1. In this particular case, x1 is 1 and y1 is 2, but never mind. Here's another point, P2, which has got coordinates x2 and y2. Now, that means that this distance over here is x2 minus x1, and this distance is y2 minus y1. So the line connecting P1 to P2 has got slope which is defined to be y2 minus y1 divided by x2 minus x1. You could say that a straight line is that which has constant slope. Let's work out the equation of this straight line. It passes through, let's say, this point and this point, or we could have taken any 2 points on this straight line. Now notice over here that if one moves 1 unit this way, then this point y moves up 2 units. So that's 2 over 1. The slope is 2 over 1. Let's get the equation of this straight line. Well, it's pretty clear that it has to be y equals 2x minus 1. Why is that? Well, first of all, notice that if x is equal to 0, then y has to be minus 1. And that's exactly the case over here. Secondly, note that whenever x increases by 1 unit, y has to increase by 2 units. And so there cannot be anything other than y equals 2x minus 1. You can apply this technique for any straight line. We're going to learn something new from this example over here, f of x equals 1 over x. When x is large and negative, which we write as x tends to minus infinity, well, f of x is going to go to 0. Then, as x becomes larger, meaning as it moves towards 0 from the negative side, then f of x is going to go to minus infinity. So it's going to get very large and negative. Let's see how the magic pen treats this. So here we have it coming from the left, moving to the right. The function is getting larger in the negative direction and becomes larger and larger until it just scoots off. Now let's ask what happens when x goes to infinity from the positive side. So as the pen moves further and further to the right, well, f of x is going to tend to 0. And correspondingly, when x is very, very small but positive, then f of x is going to tend to plus infinity. We see that it goes down very rapidly from infinity and moves off towards 0. Correspondingly, as we move back, it goes all the way to plus infinity, and then suddenly At x equals 0, it becomes minus infinity and then goes to 0. We can repeat this just once again, like this. As our final example, let's take g of x equals 1 over x squared. And let's see how this plots out. So coming in from the left, the function increases in the positive direction and then scoots off to infinity. Once x crosses 0, then it comes back from infinity and becomes smaller and smaller. It never goes exactly to 0, but it gets quite close over there, as close as you would like. The functions you saw in this lecture were rather simple to plot. In the next lecture, we're going to be dealing with somewhat more difficult functions and more interesting ones.